Bismillahirrahmanirrahim. Let's start our new topic in this course of heat and mass transfer. The topic that we are going to start now is free convection, and we had discussed these two types of convection in the very early chapters. One is what we call forced convection and other is what we call free convection. In the case of forced convection, the fluid is flown over any surface via some external means, such as using a blower or a pump or something like that. Whereas if the velocity of the fluid, of course, if we use any blower or any other device to make it flow over any surface, that would increase the velocity of the fluid. But if we are not using any external device, then the velocity of the fluid would be less, and that convection is termed as free convection. The velocities of the fluid in free convection would be less than the velocities of the fluid in forced convection, and for the very same reason the heat transfer will be less in free convection as compared to the heat transfer in forced convection, keeping all the other parameters the same. So as you can see over here, in the free convection there would be the natural convection currents, right? And in the absence of natural convection currents, the heat transfer from the object to the air surrounding that particular object would be via conduction only, and the rate of heat transfer from the object would be much lower. So there is forced convection and then there is free convection, and if there is no convection, of course it would be the case of conduction, and we have discussed those things several times in the past. We had also discussed it while discussing the Nusselt number, where we had discussed that it is a ratio of the heat transfer via convection to heat transfer via conduction. So that is the basic definition or discussion on free convection. Now the free convection takes place due to density difference. As you can see over here, that since in the free convection, there would be convection currents, and those convection currents would be taking place due to the density difference, and this density difference would be caused, or rather this density difference would be produced due to temperature gradient. So if the fluid is air, suppose, so the fluid will get heated up and then its density will become less, so therefore it will move upwards and its place will be taken by the fluid which would be colder, and therefore it would be having more density as compared to higher temperature fluid. So this is how the currents would be formed, and in fact a buoyant force would be produced. We all know what buoyancy is. You would have gone over this buoyancy in fluid mechanics course. So it is due to the temperature, due to the density difference, and of course the density difference is created due to the temperature gradient. So buoyancy force is the upward force exerted by a fluid on a body completely or partially immersed in it, right? This is the basic definition of buoyancy. Now over here, when we are talking about the buoyant force or buoyancy force in free convection, so this buoyancy force is caused by the density differences, which we already have discussed a little while ago over here. Between the heated or cooled fluid, the fluid may be at a higher temperature and the plate may be at a lower temperature, or it may be the other way around. So it may be the heated fluid or the cool fluid, which would be adjacent to the surface. Of course, we all know how convection takes place. It takes place, for example, we have seen several examples in chapters 6, 7 and 8 where there is a fluid which flows over a surface, right? And this buoyancy force is proportional to the density difference, of course, and the volume occupied by the warmer fluid. Now, what happens that when two bodies which are in contact with each other, when they move relative to each other, for example, we can see over here that that we have a surface and then we have a fluid attached to it, or it may not necessarily be the fluid flowing over a surface. It may be due to a solid contact, or it may be a solid fluid contact, or it may be a fluid contact. So so when two bodies in contact move relative to each other, of course there would be friction between them at the contact surface, and this friction force would oppose the movement. We all have gone over this friction force concept way back during our 9th or 10th grades. So over here in this figure we are being shown a buoyancy force and a friction force, and over here we can see that the buoyancy force is in the upward direction, whereas the friction force would oppose the movement. Now if the fluid is getting warmed up and it is moving in the upward direction, then friction force will be opposing its movement, since the friction force would be moving, and therefore the friction force would be moving in the downward direction. Now let's discuss this small topic very quickly. It is about the coefficient of expansion, which is the beta. Over here beta is in fact related to the density difference which is created due to the temperature differences, and beta may be written as 1 over T for a perfect gas. Over here in this expression, in this particular expression, we see a rho infinity, and then we have a T, and then we have a T infinity. So again T infinity and rho infinity would be the properties of the fluid where the effects of the surface would not be felt. So we will be discussing those things in a little bit more detail in subsequent pages. So we do not need to remember this expression by heart. I mean, the second one is relatively much easier. Beta is the reciprocal of T, where T is the absolute temperature. Where T is the, kindly note that this T which is in the denominator is the absolute temperature in Kelvin. So over here in the first expression we are only being told that, or shown that this volume expansion coefficient beta is related to the density differences which are caused by temperature differences. Now we are discussing this natural convection over vertical surfaces. In here you can see that this is the vertical surface and there is a stationary fluid which is at T infinity. So there is a stationary fluid besides this surface. Of course the fluid would be stationary since it is not forced convection, and slowly and gradually the fluid will start getting heated up due to the existence of the plate, or cool down, whatever the case is, and due to that temperature differences there would be density differences within the patch which is near to the near to the plate, near to the surface, and due to which the fluid will start moving upwards if it is getting heated up. Now, as you can see that it says over here that in the case of force convection, the thickness of the bonded layer increases in the flow direction. If we all know that if this is the plate, and if this is the direction of the motion of the fluid, then the bonded layer increases, the thickness of the bonded layer increases in the flow direction. However, unlike force convection, the fluid velocity will be zero at the outer edge of the velocity boundary layer as well as at the surface of the plate. Why? See, the fluid is stationary, right? We are not using any means to make it flow forcefully over the plate. So the fluid's velocity is in fact zero. Now, in this particular region, which is the boundary layer, the fluid, if the fluid is at a lower temperature, then it would be getting heated up, and there would be density differences due to which the fluid will start flowing in the upward direction. But the layer of the fluid, the very first layer of the fluid, which is in direct contact with this vertical surface, will be having the same velocity as that of the surface. This is what we call no slip condition, and we have discussed it a long ago during our very initial lectures. So the fluid which is in direct contact with the surface would be having a zero velocity, and if you take a look at this velocity profile, see what will happen when just like the case over here, when we move away from the plate, the velocity increases. And when we move away from the plate, the velocity increases, and there comes a time where the boundary layer ends, after which the velocity again becomes u infinity. But since over here u infinity is zero, right? You may say that u infinity, but in fact the fluid is stationary. So the velocity will increase. You can see over here the velocity will increase as we move away from the surface. As we move away from this surface, the velocity will increase because we are moving away from the surface. So therefore its effects will get lessened, will get decreased. But and then it reaches the maximum, and then it starts going down again. Why it starts going down again? Because we are reaching to a region of the fluid where it is stationary, where the fluid is stationary, u is zero. So that will have its effects again. So therefore when we move away from the plate, the velocity increases, and when we are away from the stationary fluid, the velocity will also be higher. But close to either the plate, close to either the surface or the stationary fluid, the velocities would be less, which can be seen over here in this velocity profile. When we are closer either to the plate, when we are closer either to the plate or to the stationary fluid, the velocities are less, and when we reach either the plate or the stationary fluid, the velocity eventually decreases to zero. But over here the velocity is zero due to the no slip condition, whereas over here the velocity is zero since the fluid is stationary. And let's take a look at the temperature profile as well. Over here you can see that Ts is greater than T infinity. So in fact this is the case where the fluid will get heated up. So when we are closer to the surface, the temperature of the fluid would be closer to Ts, would be higher. And when we move away from the surface, the temperature will eventually come closer to the value of T infinity. the value of T infinity. So this is what is being shown in this temperature profile over here, that the temperature is highest at 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 the surface or at the surface fluid interaction, and then the temperature gradually reduces to the value of T infinity. Kindly note that in the case of cold surfaces, means if Ts is less than T infinity, the shape of the velocity and temperature profiles would remain the same, but their direction would of course be reversed, right? So this is the formation of the boundary layer over a vertical surface. So there would be a region in which the velocity, different values of the velocities would be observed, and different values of the temperatures would be observed, and of course that region would be termed as the boundary layer. And outside the boundary layer, the temperature of the fluid would be having some value of T infinity, but it would be stationary, therefore U would be 0. Now we are coming across another dimensionless number, which we call the Grashof number. Grashof number is used in free convection, and it is similar to the Reynolds number in the forced convection. So it serves the same purpose, or almost the same purpose, to what Reynolds number does in forced convection. See over here, that Reynolds number is in fact a ratio of inertia forces to viscous forces, and if the inertia forces are greater than the viscous forces, means if the velocity is greater, then flow would eventually become turbulent after particular value. It depends upon whether the flow is taking place over a flat surface or through a pipe. This is what we have seen in previous chapters. Now the flow regime in natural convection is governed by Grashof number, which represents the ratio of the buoyancy forces to the viscous forces acting on the fluid. So over here the Reynolds number is a ratio of the inertia forces to viscous forces, whereas over here the Grashof number is a ratio of the buoyancy forces to the viscous forces, because in the Reynolds number it is the inertia forces or the velocity which sort of, you can say, or which contributes a major role in determining the type of the flow, means laminar or mixed or turbulent. Similarly, in free convection, it is the buoyancy force which is in fact moving the fluid. So therefore a Grashof number is a ratio of the buoyancy forces to the viscous forces. Grashof number is given by this expression, G beta delta T L cube over nu square, where G is the acceleration due to gravity, beta is the coefficient of expansion, as we have seen in the previous slides that it is 1 over T for perfect gases. So if it is air flowing over any surface, we will take beta as reciprocal of its absolute temperature. Ts is again the temperature of the surface, T infinity is the temperature of the fluid, and L cube over nu square have their usual meanings. So you can see over here that Grashof number is a measure of the relative magnitudes of the buoyancy force and the opposing viscous force. Means it is a ratio of the buoyancy force to the viscous forces acting on the fluid. For vertical plates, so since we have seen that we have seen various values of Reynolds number in previous lectures. For example, if it is flowing over a flat plate, we take the critical Reynolds number as 5 exponent 5. and if it is flowing through a pipe, it ranges from 2300 to 10,000. Similarly, in the case of free convection, the value of the Grashof number for vertical plates is about 109. So if the Grashof number is more than 109, the flow would be termed as turbulent. Again, as in the case of force convection, we have seen that Nusselt number, which is the ratio of HL over K of HL to K, is in fact a function of Reynolds number and Prandtl number. Is a function of Reynolds number and Prandtl number. So over here, when we talk about natural convection, that Reynolds number has been replaced by Grashof number. So the expressions would be having the same form. Instead of having a Reynolds number, we would be having Grashof number, and that product of Grashof and Prandtl is termed as Rayleigh number. So RA is in fact Rayleigh number. And we all know what this characteristic length is. It is a ratio of the area to the perimeter. And in sometimes we also calculate the characteristic length using volume over area. So we will come across those things while we would be solving the problems. So over here we are going to discuss the phenomena of free convection over inclined plates. Over here we can see that this F is the resultant force, which can be broken down into two components, one along this axis, which we may call X, means along the plate, and the other one along another axis, which we may call Y, means at 90 degrees to the plate. And this is the hot plate, means Ts is greater than T infinity, and we are considering free convection on both sides of the plate. We are considering free convection on upper side of the plate as well as on the lower side of the plate. So the flow over this plate on the upper side, because this plate is no more vertical, rather it is inclined. So we can see over here that on the upper side of this inclined plate, this Fy, which is in this direction, will try to move the fluid in this particular direction, along with movement along the plate. But due to the gravity, due to the weight of the fluid, the boundary layer will not keep on growing forever. Rather it will break, and it will take the form of those plumes. The boundary layer will take the form of those plumes. So you can see over here that the boundary layer would break up due to the gravitational force, and it will form the plumes. So those shapes are the plume shapes. So if the flow is taking place over an inclined plate, so its analysis would be a little different from the vertical plate. Over here, this is a table which I have taken from Yunus Singhal, and there are various geometries provided over here, and the second column is that of the characteristic length. So this is what I was talking about a little bit earlier, that in some cases it would simply remain the length of the surface. However, in some cases it would be the characteristic length would be calculated by taking the ratio of the area to the perimeter, and then First of all, what is this table about? This table gives us the expression of Nusselt number. Just like we had a table of the Nusselt number in previous chapters. So those expressions of Nusselt number were in the form of Reynolds number and Prandtl number for different cases, means whether the flow is taking place over a surface or through a cylinder, or if it is laminar or turbulent. So there were various expressions of Nusselt number for various set of conditions. So this is the same table. So over here we are given the expression of Nusselt number in the last column against various ranges of against various geometries and against various ranges of Rayleigh number. So over here we would be calculating Rayleigh number, which is again the product of, which we have seen before, which is a product of the Reynolds number, means Reynolds number for force convection, right? Reynolds number is for the force convection, which is the Grashof number in the free convection, and Prandtl number, right? So the product of the two is the Rayleigh number. So we are given the ranges of Rayleigh number over here, depending upon which we would be selecting the appropriate expression of Nusselt number to calculate Nusselt number, and that expression of Nusselt number will be used to calculate the value of the heat transfer coefficient. So you can get this whole table from the book, and as I have told you that I have taken it from Yunus Singhal. This problem says that the air flow through so it is air which is flowing. So the fluid which is flowing is in fact air. So air flows through a 15-meter long rectangular heating duct. So this is the 15-meter long rectangular heating duct. This is the length of the duct, which is 0.75 meter wide, and 0.3 meter high. So its height is 0.3 meters. So this airflow maintains the outer duct surface at 45 degrees Celsius. So the TS, the value of TS, the outer surface temperature of this duct is 45 degrees Celsius. So we are given TS as 45. If the duct is uninsulated and exposed to still air means just like normal air. There is no fan or blower or any other thing which is used to make it blow over the surface. So it is still air means it is just like regular air that we have normally at 15 degrees Celsius. So the temperature of air means T infinity is 15 degrees Celsius. What is the heat loss from the duct? So we have to find out Q, heat loss from the duct. So as we have seen in previous chapters of convection, that we usually calculate the properties at mean film temperature. So therefore, first of all, we have calculated the mean temperature, means the mean of average of Ts and T infinity. So it comes out to be 30, means 303 Kelvin. At which, from the same table that we have been using for so many times, which we have used for so many times in the past, we can then calculate the properties. Right? So we would be calculating the viscosity, K, and Prandtl number, and we can also calculate beta. Of course, beta is not listed over there, but we can calculate beta for air using that ratio, using that reciprocal of temperature. So the temperature is 303 Kelvin, so its reciprocal would be 0.0033. Now again, Q would be found out using the same expression of HA delta T, as we have been doing it in the previous chapters. for which we need to find out the value of H, convection coefficient, which would be found out using the value of the Nusselt number. So just like in the previous chapters we were selecting an appropriate expression of Nusselt number, we would be doing the same over here. So there are two vertical sides and two horizontal sides. So for vertical sides we would select this expression of Nusselt number, and this expression of Nusselt number has been taken from this table, as you can see over here. That for the vertical plate we can use either of those three expression of the Nusselt number. So for the entire range of Rayleigh number we can use this expression of Nusselt number, and as it says over here, it is a little bit complex, but it is more accurate. However, you are free to select either this or this expression of Nusselt number after calculating the value of the Rayleigh number. So you can follow either procedure. So if we use this expression of Nusselt number, so what we require are the values of the Rayleigh number and Prandtl number. So Prandtl number has been found out from the table. All we need to do is calculate Rayleigh number. And what is Rayleigh number? Rayleigh number is a if you go, Rayleigh number is the product of Grashof and Prandtl. So what we need to calculate is the Grashof number, and Grashof number has this expression G beta delta T L cube over viscosity square. So coming back, so we will calculate the Grashof number, G beta delta T L cube over nu square. G is of course 9.81, beta is 1 over T, which we have calculated as 0.0033. Temperature of the surface, entire surface, is 45 degrees Celsius, and T infinity is 15. Still air is at 15 degrees Celsius. This L is, if you look in the figure, this L is this length, or you can say the height of the plate, of the vertical plate, which is 0.3. You can see over here it is 0.3. So this L would be having a value of 0.3 over viscosity squared. So we get 9.99 exponent 7, or almost 10 to the power 8. So if we multiply this value of Grashof number by Prandtl number, which we found out from the table of properties for air, we get Rayleigh number as 7 exponent 7. Now if you put those values of Rayleigh number, if we put those values of Rayleigh number and Prandtl number in this expression, so we get Nusselt number as 55, and Nusselt number is in fact HL over K. Again L is 0.3, and the value of the thermal conductivity of air has been seen from that property table. So therefore we get the value of the convective coefficient as 4.8 watts per meter square Kelvin. So all we need to do now is put this value of H in Q is equal to HA delta T, and we have two such sides. We have two vertical sides. So therefore we get the Q as 13.59 watts. So the heat transfer taking place from the two vertical sides is 1313.59 watts. Now for this one, for the top surface, so what we need to do is that we need to refer to this one, horizontal plate. Now it says A, which is the upper surface of a hot plate, and B, which is the lower surface of a hot plate. So over here, if we take a look at the geometry, so the surface of air is at 45 degrees. The surface of the plate is at 45 degrees Celsius, whereas air is at a lower temperature. Right. So the plate is at a higher temperature than air. Right. So So we will first calculate this characteristic length, which is the surface area over perimeter. The surface area is you can see, I will show you, it is 0.75 over here. This length is 0.75 and this length is 15, right? If you take a look at the upper surface, it is a little bit more clear that this side is 0.75 and the other side is 15. So the surface area would be 0.75 times 15, and perimeter. So the perimeter would be 0.75 plus 15 plus 0.75 plus 15, the perimeter of this upper surface. We are not talking about this perimeter 0.3 plus 0.75 plus 0.3 plus 0.75, rather we are talking about the perimeter of the upper plate. So it would be 0.75 times 2 plus 15 times 2, right? So we get this characteristic length of the plate as 0.357 meters. Kindly pardon me for this a little bit of corrections. So we will again be calculating the Grashof number and then the Rayleigh number. Why are we calculating the Rayleigh number? Because we have to select the correct expression of Nusselt number depending upon the value of the Rayleigh number. That is why we need to calculate the Rayleigh number, for which we require Grashof number. So Grashof number is again G beta. So G is 9.81, beta is 0.0033, delta T, it would remain the same, over viscosity would remain the same. All that will change is the characteristic length now. So it would be 1.6 exponent 8. Right? So if we multiply it with the Prandtl number, we get this value as 1.18 exponent 8. So depending upon this value, 1.18 exponent 8, 1.18 exponent 8, so this value is between this range. So therefore the expression of Nusselt number would be 0.15 Rayleigh to the raised to the power 1 by 3. Right? So therefore we would be using this expression of Nusselt number so the value of Nusselt number will be calculated as 73.77, and upon equating it to HL over K, again the procedure will remain the same. It is only the values or the expression of the Nusselt number which will keep on changing depending upon the geometry. We get H as 5.4, and if we put it in this expression of HA delta T, we get Q as 1849. So this is the heat transfer taking place from the horizontal surface. From the other horizontal surface, the L would remain the same. So therefore Grashof number and Rayleigh number would remain the same. However, for Nusselt number, let me go to the, right? So it would be between it was 10 to the power 8 something, right? So now we have to take the lower surface of a hot plate, right? Because if it is a hot plate which is at 45 degrees Celsius, so the convection would be taking place between this hot plate and the air below it, right? So the Nusselt number would be 0.27 Rayleigh raised to the power 1 by 4, Rayleigh raised to the power 1 by 4. So we get this Nusselt number as 28.198, and upon equating it again to the same ratio HL over K, we get the value of convection coefficient as 2, and if we put this value of convection coefficient in HA delta T, we get Q as 707, and upon summing up those 3 Qs, in fact those 4 Qs, right? 2 from vertical sides, 1 from and 2 from horizontal sides. So we get total heat transfer as 3870 watts.